Actually, Bellman Ford algorithm is similar to the Dijkstra algorithm. Since if you learn the Dijkstra, okay, it will be Bellman Ford. Okay. So what functionalities we have used in the Dijkstra algorithm, the same functionality will be used here. But the cost will be high when compared to the Dijkstra. The complexity will be high when compared to what Dijkstra algorithm. Okay. And the main difference we will discuss between the Dijkstra and the Bellman code. The Bellman code is designed before the Dijkstra algorithm. The reason is it is having some drawbacks. So what the Dijkstra algorithm is designed. Okay. Also, some restrictions are there in the Dijkstra algorithm. The Dijkstra and the Bellman code both are what the shortest path algorithms. In the shortest path also what it is a single source shortest path algorithm. Single source means what? The problem of finding the shortest path from any starting node. For each and every pair, if you are able to find the shortest path, then that will be a all pair shortest path that we discussed applied Warsaw algorithm. So in the single source, we discussed the Dijkstra algorithm. So this is also what one of the single source shortest path algorithm, Bellman and the Ford algorithm. So we know about the relaxation function, relaxing the edge. So that is the key algorithm in the Dijkstra. The all the edges are going to be what relaxed. But in the Dijkstra algorithm, the amount of relaxation of that edges will be very less. All the edges will be relaxed only one time in that. Okay. But here the concept is very simple. The graph is given, cast is given. Okay, so we need to relax all the edges what we have to relax each. That relaxation has to be done for n minus 1 time. That is our algorithm. Very simple algorithm. Okay, so we have to relax the edges what n minus 1 times. The thing is what, but Dijkstra algorithm what based on there's a greedy approach. Okay, greedy approach means after relaxing one edge, so what is the minimum that we will pick? Okay, so that which is the minimum greedy charge. So in each iteration, what we choose one that is that adjacent edges will be what relaxed. Okay, that is a Dijkstra algorithm. But here, okay, so what is the difference that we will discuss? Used to find a shortest path from the given starting to all other. So used to check whether the graph contains the negative. So that is the main important. Another advantage in the Bellman fold is negative weight cycle that also we discussed. Okay, Dijkstra algorithm will not works if will not work if it containing what any negative weight cycle. It will occur to that negative weight. So the condition for Dijkstra algorithm means what? Assumption is the initial graph should not have any negative weight cycle. The reason is what a negative weight cycle actually shortest path algorithm we cannot apply. We should not apply. It means it form a cycle with what negative cost, effective cost, so that we cannot predict which one is the shortest distance. Okay, if I circulate that loop one time, it will give one cost. Second time, if I form a loop, it will give some reduced cost. So what as much as if you are increasing what the loop, okay, the cost is getting what reduced, but we don't know which is the minimum cost. Our objective is but minimizing the cost, so that we cannot able to find if it is contained in the negative weight cycle. Okay, so Dijkstra algorithm will not check whether it is having the negative weight cycle or not. Blindly it will be applied, so that only the initial assumption is but it is not having any negative weight cycle. So usually the Bellman Ford algorithm will be useful for what? Whether it is having the negative weight cycle or not. If it is contains the negative weight cycle, the Bellman Ford algorithm return false. False means what? I cannot find the shortest path, like that it will say. But Dijkstra did not say like that. It will give some answer, will be a wrong answer. So that only the Bellman Ford algorithm will be used in some other algorithms to check what whether the shortest path algorithm can be applied here or not. For that they will use it. For example, Johnson algorithm is that it is not there in your syllabus. Okay, actually Johnson algorithm is actually a all pass shortest path. Okay, we have only the applied version that we discussed. Okay, in Johnson algorithm they used the Bellman Ford algorithm to verify whether the negative weight cycle is exist or not. Correct. So here we will discuss so you can understand what is that. Okay, so that what the Bellman Ford algorithm can be applied even if the graph is containing the negative weight cycle. Okay. So negative edges are allowed where Dijkstra algorithm won't work if graph contains a negative weight cycle. So Bellman Ford report what false if graph contains any negative weight cycle. If there is no negative weight cycle means it will return true along with what the shortest distance from the starting vertex to all other. So it is also finding the shortest distance from starting to all other nodes. Okay. Also report what whether cycle is present or not. Negative weight cycle is what present or not. That also what it is. What it is. It is present. It will not give the answer. It is not present. It will give the answer. That is it. So as I told already told, it's a very simplest algorithm, Bellman Ford. If you understand the relaxation function, relaxing the edge. What do you mean by relaxing the edge? The algorithm will be simple. The relaxing the edge means the two vertices, okay, and one edge will be there. Okay, for the two edges, okay, already shortest distance are recorded. Okay, and edge cost will be given. So based on relaxing edge means based on that edge, okay. So what is the change from that x to y? So what is the changes there in the distance of v? So the relax will be applied for what? U and V, two vertices. Okay, so the U distance is what shortest distance is recorded. V shortest distance is already what recorded, and the distance, the cost between that U and V, that is a direct cost is there, and that is U, and this is V. Okay, some cost will be there between the U and V. Okay, for the edges between the U and V. Okay, that is the cost. Okay, C, this is what D, U dot D and V dot D. By relaxing this edge, what is the changes in the destination vertex? Okay, that will be get changed. It means that suppose if this cost is what 6, this distance is what 7, okay, and this cost is what 2, 2 plus yes, this is shortest distance recorded as what 2. So 2 plus 6, if it is less than the existing shortest distance, you have to update, otherwise no need. That is a relaxation. But here it is what 2 plus 6, 8. This is 7. So no need of what relaxing. Okay. Suppose if this is the 4, so this is the 6 total cost. So through this path, we are getting the shortest distance as what 6. Already recorded shortest distance is 7. So I need to what update. So updating means what? This need to change it to what? 6 shortest distance. Now V parent is should be updated with what? This U. So this two updation is getting what updated. So V dot D, this one is greater than U dot D plus this cost, edge cost. Then I have to update V dot D and V dot parent. That is a relaxation. Okay. So the thing is what in the Bellman Ford, very simple, see that algorithm. N minus 1 times N is nothing but the number of vertices. So N minus 1, this is the main loop. N minus 1 times all the edges in the graph need to be what? Relaxed. That's all. So for I equal to 1 to n minus 1, for each edge u comma v in the edge list, I need to relax it. This is algorithm. So if I n minus 1 times, if I relax the edge means what? It will find the shortest distance, sir. Like that you can ask. It may be or may not. It means that negative weight cycle is exist Okay, the distance will be calculated. Okay, but sum of the cost will be the negative. Okay, the shortest distance will not be found. Okay, so it means that and some of the edges is what remains and unrelaxed, is not relaxed. So in that case, we have to what verify. The last iteration, nth iteration is a separate for loop. So here that for loop is just checking after relaxing n minus one times, is there any edge present, okay, without relaxing it. It means that that condition relaxed means what the condition should be what false is, that is this distances should be less than what, sorry, should be greater than what this shortest distance, like that it means it is a relaxed edge. Okay, so the vertex is not getting relaxed, this condition is a false, then it means that what the shortest distance are not able to found. So in that case what we are checking what false. So this is the nth iteration, the same code here. Instead of calling the relax function, we are checking that condition. So that d dot v dot distance is greater than what this one, it means that that edge u comma v is not relaxed. So not edge that not relaxed means what the shortest distance is still not found. It means that it is contained in negative eight cycle. So it is returning what false. Correct. So that is the key concept of what Bellman fold algorithm. Okay. Just here I presented an example step by step. Okay. You see that you can understand. Okay. You see this example which is there in the book. The same example I have taken. Okay. So the starting. So before that one function is an initialize single source. Initialize single source means what? What is the starting vertex that will be given? Okay. So the starting vertex distance will be updated with what is 0. So all other vertices distance will be what infinity, that parent will be the nil. Okay. So all vertices in the graph, okay, whose parent will be initialized with the nil, okay, and except the starting node, okay, all other vertices, okay, distance will be updated with what infinity. Starting node distance will be the 0. That is initialization. Okay. You take this is the initial what graph. So the starting node we have assumed as what? Yes. Okay, the starting node we assumed as what? Yes. So whose distance is what initially 0. All other vertices distance will be what? Infinity. So far the shortest distance is what? Infinity for all other nodes. So S2 the distance indicate S to T the shortest distance infinity, S to X shortest distance infinity, S to Y like that. So the distance indicate what? From the starting node to reach the corresponding vertex. What is the distance? Okay, there are n minus 1 iteration, n is the number of vertices. All edges need to be relaxed n minus 1 times in the particular order. So all edges I told now simply you we told what all the edges. You can take in any order. Okay, in any order you can take the edges. That is not a matter. Okay, and for example, n equal to 5, no need to relax the edges for 4 times. So assume the order of edges. So in this order, we are going to what relax it. So I have written all the edges present in the graph like this. Okay, you can write in any order. It is not a matter. Okay, so now I'm going to start that iteration. The first iteration I equal to 1. So during that I equal to 1, that's n minus 1 iteration, I equal to 1, 2, 3. So this table I'm going to maintain whether when I equal to 1, that edge is getting relaxed or not, like that we are going to check it. Relaxed means what? The update is done, then it is a relaxed. Update is not done means what? Already the edge is what? Relaxed. So no need of for relaxing. Okay. So the relaxation is done on that edge or not, that I'm going to mark. If it is done means what? There will be changes. Correct? See this. I'm going to start from the t comma x. Okay, t comma x. So t comma x means what? This edge. Okay, this edge. Whether you wanted to relax the t comma x, this edge, this cost is what? Infinity. From this graph, I have to apply all the edges. Okay, so infinity plus 5. This is already what? Infinity. So in a node, I have written that as shortest distance. You see that. Okay, infinity. So infinity plus 5 infinity. Okay, no need of relaxing. Next t comma y, t comma y. So infinity plus 8 already infinity, no need. Similarly t comma z, no need. X comma t. So nothing to be what changed. Okay, but S comma T. So among this, okay, which edges are getting relaxed means only the S comma T and the S comma what Y. You see that S comma T here, S distance is the 0, T distance is the infinity. So 0 plus the edge cost is 6. 0 plus 6 is less than what that infinity. So need to what change, relax it. So that only we are done here. 0 plus 6 is less than what infinity, so update it. Which one to be updated? T dot distance is updated with what 6, and the T dot parent is going to be updated with what s. Okay, so the parent used to form a path. Okay, the distance is used to find the shortest distance. Okay, you see this t comma x, sorry, s comma t. So it is getting what relaxed, so that s and 6. Similarly, what this s comma y, last one. So s comma y is what 0 plus 7 is infinity. Change it. So this will be changed to what 7, and this is changed to what 6. Okay, so that changes happened here. So 7 and 6, and the corresponding changes are there. Only two edges are relaxed. If you go through all other edges, nothing will get what relaxed. No need to what change anything. Okay. The next iteration, you have to repeat this for what 5 times. That's all. Okay. In the next iteration, again I have to check all the vertices. Okay, edges. T comma x. Among that, so the changes happened for what t comma x, t comma z, and then what y comma x. So other things are not getting what changed. Okay, first t comma x means 6, 5. So you have to see in that previous graph here. So 6, 5, and then what infinity. 6, 5, infinity. So 6 plus 5 is 11. 11 less than what infinity. Update. This is what 11. Okay, so after relaxing the t comma x, the thing is what the x is changed to what t and 11, correct? T comma x distance is changed to what t comma 11. After that t comma z, t comma z means this is the t, this is z, so that it will be changed to what 6 plus minus 4, 2. So this will be changed to what 2. So that is happened here. So which one is changed in z? So z parent is updated with the t, and then what? That is a 2. And one more edge y comma x. Okay, y comma x means here you see that y and x. X is already what 11. So now y is what 7. 7 minus 3 is 4. 4 is less than the 11. So it will be again changed to what 4. So that only I draw two tables. After relaxing the t comma x, x value changed to what 11. But while relaxing the y comma x, again it is getting changed. The parent is getting changed to what y, whose cost is less. Okay, distance is what 4. Okay, if you check other edges, okay, so nothing will have what nothing will need what relaxation. So you can kept unchanged. Okay, so next iteration 3, we are going to repeat the same procedure. So during I comma 3, the same procedure will be applied. So now what only x comma t is getting what changed, x comma t. What is the x and what is the t here? So 4 minus 2 is the 2, but it's already what 6. So we need update. So this will be changed to what 2, and the t parent will be updated with what x. So see that t parent is x, that distance is what 2. Like that we change it. So this is the resultant graph. So at the end of the third iteration, this is the resultant graph. So the next fourth iteration. To apply the fourth iteration, I need to consider this graph. Okay. So in that graph, okay, only what t comma z need changes. Others already what relaxed. So t comma z. See that t comma z, t z. So 2 and minus 4 minus 2, it is already what 2. So it is going to change to what minus 2. This parent is changed to what t. Okay, so that is going to be happen on what? The Z. So Z parent is T and the cost is what? 2 minus 2. Whether I wanted to continue the iterations, no need. If that the graph is not having any negative weight cycle, the problem will be solved in the n minus 1 times. You will get, definitely you will get what? The correct shortest distance. Suppose if you are having the negative weight cycle, when we are verifying the next iteration, it will be what? Found. Okay, see that after at the end of the fourth iteration, this is the graph, this is the shortest distance s to t, like that. So what is the conclusion here is, at the end of the n minus 1 iteration, need to check all the edges are relaxed or not. For example, after fourth iteration, in this example, after fourth iteration, okay, all the edges are what? Relaxed. You see that when I equal to 5, like that, that is what? Next iteration. If you repeat the same, all the edges, if you are checking, the result will be the n no only. Okay, so already what all about relaxed, no need of what changing anything. So changes are not required for what any edge. It means that the problem is solved, is not having the negative sign. In nth iteration, if you need some edges to be what? Relaxed, it means that the problem is unsolved. So we cannot find the shortest distance. It means that it is having the negative weight cycle. Okay, so the algorithm will return true with the final table. Okay, the following shortest path. So what is the shortest path means what? So for the x, t is the parent. For the x, sorry, for the t, x is the parent. So x to t. Okay, x to t. So what is the distance? Okay, for the t, distance is what? 2. That we have to mark it. Okay, and then next, for the ya, x is the parent. Okay, for the ya, sorry, again, for the x, y is the parent. So y to x. Okay, and then I need for the y, s is the parent. So what? S to y, s to ya. And then for the z, t is the parent. For the z, t is the parent. Okay, so what is the corresponding cost shortest distance we have written here? Okay, so this represent what? The distance between the edge cost between the x comma t, y comma x, s comma y, that is written. So if want to find the shortest distance to any other vertex, this is a path as well as what? Shortest distance. If I want to reach s to t means what? I have to travel from s to y, y to x, and x to what? T. The distance will be the 7 minus 3 minus 2 equal to what? 2. Okay, we got this. So this is the final. We got the result. Okay. So if you continue for the I equal to 5, your result all should be what? N. Then only your result is correct. Okay. If any of the edges required what? Relaxation, then your problem is unsolved. Okay, keep it in mind. So this is what? Bellman fold algorithm. So the result is what? By implementing the Bellman fold algorithm, you have to say it is not having the negative weight cycle and the cost is like this. We have to print. Okay, suppose if you give the negative a graph with what? Negative weight cycle, so it should report the error. Error means what? The graph is containing the negative weight cycle, so that shortest path cannot be determined. Like that, you have to what? Print it. Okay. So this is the Bellman Ford algorithm. Okay, the code I have already shared. Okay, this is the algorithm. The same thing we have implemented in the code. Okay, just to go through the concept implementation. Okay, next class, for the next two classes I planned for the uh, flow problem, network flow problem, which need the implementation, and the fourth unit, the introduction to the approximation algorithm, and one example problem in the approximation algorithm that we will discuss. Okay. If you have any doubt now, you can ask.